Hey all your sons, this is Pradesh Chaudhary Open Group. The last lecture on electrostatics was an introductory one in which I talked about charge, its properties and charge density, and also did few questions on charge density. The primary purpose of taking those questions on charge density was to get a feel how to take element and do the integration, which is very vital in this chapter. So now let's get started with the main part of the chapter. Is a real starting point of the chapter is the Coulomb's law. Before Coulomb, there was a famous scientist named as a Benjamin Franklin. He did a lot of experiment on static electricity, static charges, and established with the experiment that the like charges repel and unlike charges attract. Coulomb did one step further and found the amount of the force the two charges exert on each other. So the setup was very simple. That is a torsion pendulum. Let's first try to understand torsion pendulum. So this torsional pendulum is something like this. This is a torsion wire and that is a pendulum. Pendulum could be a sphere or could be disc, and in this case that is a rod. In the rod, this has to be center mass so that this rod is in the horizontal level always, and there is some one ball attached here and one ball attached here. If I manually twist this, and obviously as I will rotate this, I am applying external torque, and against that external torque, a restoring torque develops in this wire. So if I rotating and holding it, the two torques are balanced. My torque applied by my hand and the torque applied by this torsion wire. But as soon as I release my hand, the restoring torque will try to bring it back to the initial position. But by doing that at the equilibrium position, it will have some kinetic energy that it will keep on rotating. So now in the setup of Coulomb experiment, this is a torsion wire and there is a one ball here, say A, and one ball here is A dash. So he gave a charge to one of the balls, say A, and brought another charge ball here. So because of the forces between them, he kept the two charges of the same sign. So because of the forces between the two spheres, a torque develops. If the force is here, so it will try to rotate that, and the strength of that force will be measured by how much this torsion wire or how much is this rod rotated. If it rotates more, mean the force between the two balls was more. If it rotates less, the force was less. And he made variations, like he changed the amount of charges, he exchanged the charges, he changed the distance. So finally found that the magnitude of the force between the two charges depends on, number one, is directly proportional to the product of two charges, number one, and it directly proportional to product of two charges. That does not mean it does not depend on the value of one charge. It is the cumulative strength of the two charges, and is inversely proportional to the square of the distance between them. That is a primary basic thing of the Coulomb's law. It's kind of an inverse square force. Most of the long distance forces are inverse square force. So Coulomb law is a inverse square force, and before that gravitation law was discovered. So it was people gradually accepted that law. So now what are the finer points about the Coulomb's law? Let's go. So properties of Coulomb law. Suppose we have these 2 point charges. So two very basic properties of Coulomb law is, number one, that it is applicable to only for the point charges. The charges, point charge, I mean it doesn't has a large dimension, it is point charges. So for that thing, the law that I'm going to state, that is valid for that. And second thing is that the force between these two charges acts along the line joining the two charges. It does not act like that, it does not act like that. It can be attractive or repulsive, but it will act along the line joining two charges. So number one, it is valid for point charges only, and the force between them acts along the line joining the two charges. So here, this is Q1, this is Q2. They are separated by distance R. On Q2, the force exerted by Q1 is F21, and on Q1, the force exerted by Q2 is F12. So obviously these two has to be equal and opposite for the neutral third law. force between two point charges in isotropic medium. First, let's try to understand what is the meaning of an isotropic medium. So isotropic medium is a simple thing, a medium which have a same property in all direction, that is the isotropic medium. And opposite to isotropic medium is anisotropic medium, in which the medium has a different properties in different directions. So in electrostatics, if we write the medium, so by default our meaning would be the medium is isotropic. So here the two charges Q1 Q2 are separated by R, they explain some force. Coulomb law says that this amount of force depends on the product of charges and the inversely proportional to the square of the distance between them. So we have two charges separated by certain distance, and I place suppose in air. Now keeping the charges same and the separation same, I kept them in water. The force immediately reduces, or maybe in some other medium the force changes. So there is some role of medium, there has to be some role of the medium. So if I write the force on Q2 by Q1, so there must be two things that are exerting force on Q2. One is obviously Q1 and other is the medium. When I change the medium, force changes, and that changes basically because of the medium. So force on Q2 by Q1 is always the same. Obviously the separation must be same and the amount of charge has to be same. But if I keep medium change, comes a different force by the medium, so net force changes. So right now they are placed in some isotropic medium. So now even if they were placed in air, Q1 would have exerted the force. So first of all, the force exerted by Q1 on Q2 by Q1. So let's have this thing, vector R, that is the position vector of Q2 with respect to Q1. R has a tail at Q1 and head at Q2. And let's have this unit vector of this vector R, so R cap, the direction of this vector R. So obviously vector R has that unit vector R cap is vector R by the magnitude of vector R. So that is R cap is equal to vector R by R, and the force on them, the force on Q2 will be along the line joining them. So this is F21, force on Q2 by Q1, and it has a magnitude 1 over 4 pi epsilon naught Q1 Q2 by R square, and direction is along the line joining them. I have chosen them to be of like charge, so that is a repulsion in the direction of R cap. The force on Q2 by Q1 is 1 over 4 pi epsilon naught Q1 Q2 by R square R cap, and that is the constant of proportionality. And you know one more thing, that this constant of proportionality is also depend on the choice of our units. So right now in the MKS units, this constant of proportionality is 1 over 4 pi epsilon naught. And this 1 over 4 pi epsilon naught has a numerical value 9 into 10 to the power 9 Newton meter square per Coulomb square. And epsilon naught is called the permittivity of free space, as a value 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. Why it is called permittivity of free space, that you will learn a bit more when you will understand about what the electric field is and how does that propagate. So now, and this is the force exerted by on Q2 by Q1, and this is the force that does not change on change in medium. So if the forces were in air or in vacuum, so in the vacuum there was no medium, so that was the net force. So in free space or in vacuum, this force would have been the net force on Q2, because now there is no medium, so medium will not exert a force. Now to understand the role of the how does a medium exert a force on charge, we need to understand a new concept that is called the relative permittivity or dielectric constant of a medium. Relative permittivity of a medium or dielectric constant, it's similar to refractive index of light. Like greater the refractive index of medium, smaller is the speed of light in that medium. Refractive index of a medium is equal to the speed of light in free space divided by speed of light in that medium. So greater the refractive index, slower the light will travel in that medium. So similar to that, there is a relative permittivity. Obviously light is an electromagnetic wave, so this epsilon is nothing but the electrical part of that refractive index. So let's try to understand one thing. Suppose I have two charges Q1 and Q2. They are placed in free space. You can assume air to be close to free space, and in free space separated by a certain distance, and they exert a force, say F naught, in free space. Now these two pair of charges, the same pair of charges separated by same distance, now if they are placed in some medium, they experience a different force. So I want to define an index for the medium, so that how with that index the force changes. Suppose the relative permittivity of that medium is epsilon r, and in that medium, if now they experience a force F, that is a net force, the contribution of medium is also there. So epsilon r is such that this is equal to F naught divided by F, or F is equal to F naught by epsilon r, and this epsilon r is greater than or equal to 1. So greater is the epsilon r, smaller the force will be in that medium. So now I can formally write that thing. So epsilon r of a medium is net force on Q2 in free space divided by net force on Q2 in that medium, or to be more elaborately, the net force, net interaction force between the two charges in free space divided by net interaction force on two charges in that medium. So we can also write the net force on the net interactive force on two charges in the medium as a net interactive force in free space divided by relative permittivity of that medium, and this epsilon r is always greater than or equal to 1. In this chapter, here I am introducing this dielectric constant, and in all other cases for this whole chapter we'll take the epsilon r to be 1. The medium would be the air or the free space. So now coming back to this diagram, see here. This is Q2, this is Q1, this is the position vector of Q2 with respect to Q1, that is R, and R cap is the unit vector as explained. So this F21 is the force on Q2 by Q1, and because of the medium, the Q2 experiences a force F2 medium, and the vector sum of this F21 and F2 medium is the F2 net. You can see that this F21 is in this direction. This F21 is because of Q1, and because of the medium, the net force is smaller than F21 in the same direction. So obviously the force because of the medium has to be in the opposite direction. So now I can write net force on Q2 is equal to net force on Q2 by Q1 plus force on Q2 by medium. So now that I can write F2 net is equal to F21 plus F2 medium. In the previous PPT, I had written F21 was 1 over 4 pi epsilon naught Q1 Q2 by R square in magnitude. And I told you that that is the part that does not change with the medium. So even in the free space, that was net force because there was no medium. So the only force exerted on Q1 in free space was F21. So F21 is the same thing, 1 over 4 pi epsilon naught Q1 Q2 by R square R cap. So F2 net is 1 over 4 pi epsilon naught epsilon R Q1 Q2 by R square R cap. Now let's go to next page. So F2 net, we had written this, F2 by the medium is F2 net minus F21. F2 net was 1 over 4 pi epsilon naught epsilon R Q1 Q2 by R square R cap, and F21 is equal to 1 over 4 pi epsilon naught Q1 Q2 by R square R cap. So now just simplifying this thing, and we can get the expression for the F2 medium is minus of 1 over 4 pi epsilon naught 1 minus 1 upon epsilon R Q1 Q2 by R square R cap. You see that this epsilon R is greater than 1. So this whatever is in the bracket, that is a positive. So the direction of F2 net is opposite to R cap, and that is because F2 net is smaller than F21 in the same direction. So F2 medium has to be opposite to F21 or opposite to R cap. There are two like charges Q and Q2 placed in free space exert a force 24 Newton on each other. So here, suppose this is a Q1, this is Q2, and they are separated by certain distance. So I am taking force on Q2, so this is 24 Newton. This is in free space. And now the same charges. And now the same charges are kept in a medium of dielectric constant or relative permittivity epsilon r is equal to 3. So what will be the effect of that thing? The force exerted by Q1 on Q2 will not change. That will remain same. So that will remain 24 Newton as it was earlier. This is the force on Q2 by Q1 will remain same as 24 Newton. The effect of this medium would to reduce the net force by the same amount, that is epsilon r. So F net will be the force in free space divided by that epsilon r. So F net will become how much? That will be F21 by epsilon r. F net, that is a F net in air divided by epsilon r. So F net in epsilon r. So this is 24 by 3. So that is 8 Newton. So if 8 Newton is in the direction of F21, so what force I should add vectorally to F21 to get the 8 Newton? So obviously that force has to be 16 Newton in the backward direction, like this. So here the net force on Q2 is equal to 8 Newton and force exerted on Q2 by medium is 16 Newton in the opposite direction to that 24 Newton. Okay. And now other properties of Coulomb force, that it is a conservative force, and if it is a conservative force, it will have a potential energy. So we can have question related to conservation of mechanical energy. It is a conservative force, hence it has a potential energy, and the force between 2 point charges acts along a line joining them. It can be repulsive, it can be attractive. So it is a central force. See, what is central force? Suppose I have this charge Q. Let me keep this charge as a fixed charge, and suppose another charge moves like this. It approaches here and it goes like that. Suppose this charge is somewhere here, somewhere here, somewhere here. At different positions of this charge, the force exerted by this capital Q on this would be along this direction, along this direction, along this direction. You can see this force is always directed away on a line from Q. If it was a negative charge, so that was directed towards. So that is kind of called a central force. So let's take one position of a central force. At this position, this is the force, and this is a small q, and the position vector of small q with respect to this capital Q is this. And you can see that the torque due to this force about Q, the torque is R cross F. So in any position, R is parallel or anti-parallel to F. So torque is 0. And if torque is 0, so that's angular momentum is conserved. We had written the properties of and we know that this torque is dl by dt, rate of change of angular momentum. So if torque is 0, so L is constant. So that is a very important aspect of Coulomb force, that the angular momentum of a charged particle about other charged particle that is exerting a force on it is conserved. Okay. And now superposition principle. So what is superposition principle? So superposition principle says that suppose there are a lot of charges there, and there's another charge, so force on one charge due to assembly of other charges. So when we apply a force on one charge by other, that force does not depend on the presence or absence of the other charges. So if it would have depend, then the superposition principle will not work. So how does it work? Suppose I have a q1, q2, q3, q4 charges, and there is a capital Q charge. When q2, q3, q4 were absent, the force on capital Q was by q1 was F1. Similarly, when q2 was only there and the other force were absent, the force on capital Q was F2. So superposition principle that now if all the charges are present, the force on capital Q by Q1 will not change. If it does not change, so now the net force is the vector sum of these individual forces. So net force on this Q will be written as a F is equal to F1 plus F2 plus F3 plus F4. So that is superposition principle. So that's all for Coulomb's law. This was a theoretical lecture. In the next lecture, we'll do the numericals on Coulomb's law. So thank you.